Alright, today what I thought I would do is work on one of these Esri web courses that I still have on my learning plan, and that is the Introduction to Spatial Data. And it should take me about an hour and a half to do this. Probably going to take me a little longer because I'm going to talk my way through it and be a little more deliberate with my actions. So I've already logged in to my lesson plan, and I will move this window out of the way so I can reveal my desktop and show how I go about launching things and kind of demonstrating how to get started. It may be a little boring and it may be a little routine, but I'm doing it just simply so people can have an idea of what to expect and what to look for. So I'm going to go ahead and launch my course, and I'm going to use the ArcGIS Pro 3.1 option. I have updated my software to the 3.2 level. I think I said 3.2. So I'm going to choose that option. So anybody using the software needs to choose the software that's best suited for them. So I am going to read through these things so we understand where we're going with this. So we do have two goals: to describe two spatial data models used to represent the real-world features and phenomena, and then to use ArcGIS Pro to explore raster and vector data. The software requirements are Pro 3.2, the basic, standard, or the advanced, and if you're enrolled in EES 202, then you will have the advanced edition of Pro 3.2. I'm going to go ahead and download my training data and accept the license agreement. It's about 70 megabytes, so it should not take too long. And I am going to put this in a folder somewhere. I already have a training folder set up, I just need to find it. So I am creating a folder inside of my EES 202 folder. It's called ESRI, and inside that ESRI folder I'm putting another folder called Training Data, and then I'm going to download and extract that file that I have over from ESRI, and I'm going to put it in that folder and then extract the files. And then once those files are extracted, it should display them for me. Alright, so here we go. Here's my ESRI folder, here's my training data folder, and here's my spatial data intro folder. So the important thing is, when you download data, remember where you put it. Another recommendation is to create yourself a directory structure so that everything makes logical sense and you don't have to search all over your hard drive to find where you put things. So it's a good idea. Now let's go ahead and look into this folder. So inside this spatial data intro folder, we have the import log index, we have raster data. So there's several raster files. This is a TIFF world file, a TIFF file. We've got a database here of thumbnails. We have another TIFF world file. This is basically a text file. I'm going to open this up and show you. Open with Notepad. Actually, we're not going to edit it. And so in this file, what we have basically are the coordinates of probably the upper left and lower right corner. And then we have this looks like a latitude longitude coordinate in decimal degrees, so we're going to find out what all that means here in a minute. But don't mess with those files. I just wanted to let you look at those to see that, let you see that those were a text readable file. The TIFF is not. let's go ahead and dismiss this, and then we'll go into, oh, the other thing I want to point out is always look at your left sidebar. You have a menu over here, your overview, an introduction, spatial data, how long the unit module will take, how many portions of that module you have completed, and then you'll have a conclusion. And usually in between you'll have some type of brief quiz to take. So characteristics of spatial data. Many people think only think of maps when discussing spatial data. While maps are a start, spatial data is much more. Spatial data, also known as geographic information or geographic data, can be represented on a map of real-world features and phenomena. However, it can also be any information with a location attached to it, whether a map or not. And we have an example of a Colorado driver's license. We have height, weight, the type of class, the class of the license number, and then we have this person's date of birth, the color of their eyes, their gender, their address, their name. So there's lots of location and attribute information on this little card that people carry around in their wallet or whatever. Spatial data is part of everyday life. At work, you might work with customer addresses, tracking the delivery of packages, or analyzing patterns of sales across a region. Outside of work, mobile devices can use location services to find nearby restaurants, businesses, provide turn-by-turn navigation, or track exercise activity. Continuous phenomenon. There are many ways to categorize GIS data, but one of the most basic is whether data is discrete or continuous. Discrete data represents real-world features that have well-defined boundaries. A discrete feature is distinct from other features around it. For example, a river is a discrete feature. You can be in the river or out of the river, or half in and half out of the river, but there is a distinct place where you stop being dry and begin getting wet. So I would use another example actually, and this map shows the San Diego Convention Center and uses discrete data to show the locations of buildings, streets, and trolley lines. So we can see that these boundaries here, where I'm drawing, highlighting with my cursor, those, if I'm reading this correctly, those are property boundaries. And so property boundaries are definitely discrete features. You're either on a piece of property, or generally you're on another piece of property. Either you cannot be, you can straddle property, right? So one foot's in one property and one foot's in another property, but it's either in or out. There's no gray area in between property boundaries. Continuous data represents real-world phenomenon that do not have well-defined boundaries. An example of continuous phenomenon include elevation, temperature, or rainfall. Sure, you might have a thermometer in a place that tells you what the temperature of that place is, but the reality is that temperature is distributed across an area, right? So what you're basically doing is getting the temperature from that point, and then your brain is saying, well, this is probably the temperature for everything else around it, and that may or may not be true. So that's just one data point. You know, you go a half mile one way or a half mile another way, or even if you walk out into a parking lot that has a different kind of surface material, like concrete versus asphalt, you may have a temperature change. Or the further you get away from a building, or closer you get to a building, because of the reflective and absorptive nature of the building materials, you might also have another temperature. So temperature is going to vary. In each of these examples, there are no distinct places where the phenomenon simply stop. Values may change abruptly, you know, like you come to a cliff and you you have a cliff at an elevation of 900 feet, then you step off of it, and then when you stop, you're 400 feet lower and dead probably. But you know, that's like, you know, part of geology. But the phenomenon continued to be measured. One way to determine if the data you are evaluating is discrete or continuous is to consider if taking an average of the values would make sense. If it makes sense to take an average of the values, such as average precipitation, average depth, or average humidity, then the data is continuous. If it does not make sense to take an average of the values, such as building type, street name, type of tree, then the data is discrete. So, for example, census data is discrete. So you can gather census data at the census block level, the block group level, the census tract level, the county level. And so while you might be able to take the average of the values within each tract, the reality is the tract itself is discrete because there's only one value for that tract or block or block group. So for example, you cannot add two zip codes together because that doesn't make any sense. If you can do a mathematical operation on the number, then it's probably continuous. If you cannot do a mathematical operation on the number, then it's probably discrete. So like you don't do mathematical operations on telephone numbers, you don't do mathematical operations on zip codes, those kinds of things. So there's a little bit more entailed in this discussion than what they have given you here. The types of analysis and visualization you can perform with ArcGIS may depend on whether the data you are using is discrete or continuous. So it is useful to know how to differentiate between the two. Consider the following data descriptions and determine if they are discrete features or continuous phenomenon. So annual rainfall is definitely continuous. Roads are discrete because you can either be on the road or off the road, but you cannot be sort of either way. A slope is continuous. Ocean temperature is continuous. Voting districts are discrete. You're either in the district or you're not within the district, right? Utility infrastructure such as a gas line, electricity line, or a water line is discrete. You're either in it or you're not in it, or Addresses are discrete. You can only have one address, right? That's how our mail gets to us in the United States. Now I understand things are complicated once you go to some other areas of the world, but in the United States we have discrete addresses. And then soils are discrete because we might have soil boundaries, but the reality is the chemical composition of those soils. Well, I'm talking about it like it's continuous, but that one's kind of dodgy in my mind because I've done a lot of soils work, and the soil, while we like to think that soils, you're over here, you're going to step and you're going to be in one soil type, and over here you're going to be in another soil type. It doesn't exactly work that way. Not in the real world, because there's usually chemical and differences and soil differences. Moisture differences and temperature differences and differences of composition that kind of gradually change over distance, and it's really rare to have a soil where you're just like, it's this soil here and this soil there. But we're going to go ahead and play along with ESRI's game here. Alright. Quizzes test the knowledge and skills you have learned in each section. You must correctly answer 2 of 3 and pass all section quizzes to receive your course certificate. If it makes sense to take the average of a value, the data is continuous. Okay, I think they told us that was true. If you can do a mathematical operation on it, it's probably continuous. Which attribute or feature type can be represented as continuous data? Well, let's see. Hydrography is basically the mapping of the ocean, mapping of water. So I'm going to say a soil type is going to be discrete, land use is going to be discrete, ocean depth, that's basically bathymetry, and that's like an elevation, so we know elevation is continuous, so I'm going to go ahead and go with ocean depth. Hydrography is kind of related to figuring out the mapping of of water bodies. Hydrography can be freshwater or saltwater. It can be ocean or seas or lakes or whatever. So, and that's just the science of it. So I'm going to go ahead and go with ocean depth. Spatial data is any data that includes information about the location of a feature or phenomenon. I'm going to go ahead and go and say that's true. And let's submit and see what happens. All right, we got them all correct. So it's this kind of stuff right here that when I go over it, I'm hoping helps kind of analyze why some answers are better than other answers. I'm probably not going to get them all right, because sometimes you can bring too much information to a problem and then it confuses the problem. All right. The vector model represents discrete objects on the surface of the Earth, such as streetlights, roads, and buildings. So what we're talking about is streetlights are points, roads are lines, and buildings are polygons, just as they say here. So I didn't even read ahead. So it says click an item below. A point is a single coordinate. A line is made up of two or more coordinates. And so this is a vertice. So we have an endpoint and an endpoint. Sometimes these are referred to as nodes. So you have a node here, a node here, and a node here. You have 3 vertices, 3 nodes, 2 line segments. So here we have 5 line segments. We have a polygon. We have 5 vertices, and otherwise known as nodes. And we may have a starting node and the ending node be the same node. So that kind of comes into play too when you're mapping, because the software keeps track of the first point you put down and the last point you put down, and if they're coincident, then they become the same point. So coincidence mean they're the same. There's one point on top of another point, and there can be, for analytical purposes, there can be 2 points right there. So it gets kind of complicated when you have a polygon, because there's potentially one point is the endpoint, or the starting point and the end point. And then you have this shaded area. So you can have lines that connect like this, like a road segment, for example. Like if you have a road that goes to a park, this would just be a line, 5 line segments, and then you'd have a line that goes off to the exit or something. And then this may not have an area inside of it. So you also have to kind of consider what the application of the geometry is. So now we have a vector map. So we have points, lines, and polygons. Points, lines, and polygons are composed of both geography and attributes, which provide additional information about the feature. The following graphics show how vector attributes are stored in a table. So we have a table, we have an object ID. To give a little bit more narration to this, you never want to change or alter the object ID or the shape ID. Regardless of your ability to do that, you can export these tables to Excel sometimes, because that will often provide you a way of manipulating the data outside of Pro, but you do not want to alter or modify anything about these 2 special columns here. Then you have description, what it is, lake, glacier, lake, pond, embayment, wetland, whatever. The name of it, like if it's a national park or state park or whatever. How many acres? The shape length. So the shape length is basically the perimeter. And then you have the shape area, which is measured in probably, I don't know, here it could be square miles or square feet or square meters. You just would have to go back and look at and find a unit that has these numbers make sense. Usually these numbers and these numbers are going to have the same units, but honestly I can't really tell. This is probably meters or feet maybe. So hopefully there's a data dictionary that tells you what the units of these values are. Alright, whoops, I think I need to go back, because I think, yeah, there's more stuff. Okay. Yeah, it's attributes for vector data are stored in each feature. Each row or record in the attribute table represents one feature. So you're going to have one row in your attribute is going to tie in with one feature. You're not going to have Generally on spatial data, you're not going to have one row, more than one row per feature. Each column represents a field or a attribute or a variable. And they could be numbers, dates, text, links to websites, multimedia links. These are automatically generated. That's why you have to leave them alone. These three, like description, name, and acres, are usually user defined. And then the shape length and shape area. Anytime you see something like the shape length, shape area, shape ID, whatever, those are usually automatically generated by your spatial database. And you should leave those alone as well. If you need to have these converted into a unit that you can use for something else later, then what you need to do is create yourself another field and then populate that field by using a mathematical conversion to take that value and convert it to the value that you need it for it to be. So like if this was meters and you need feet, then you should have a field out here called length underscore feet, and do your mathematical conversion to convert this value into feet, and then populate that box with that value and do the same thing for the field. That's how that basically works. Don't modify these. Create a new field, modify that field. Alright, I'm going to let you watch the video and then I'll be back. Alright, now we have another quiz, but they're presenting us with some scenarios. When you're deciding what to use in a map, you should consider the scale and purpose of the map. Because this helps us choose what geometry type might meet our needs. The following information to choose which type of geometry to use for the given scenarios. Note, small scale maps show large geographic area with few details. Large scale maps show a smaller geographic area with more details, for example, a neighborhood or a small town. A way to remember the difference is that a building feature on a large scale map will appear large and detailed, while the same building on a small scale map will appear small or disappear altogether. Okay, let's go into that a little bit more. Okay, so what we have here is some numbers. So this is a representative fraction. That's what RF stands for. So we have a 1 divided by 1200. And sometimes you'll see that on map as 1 to 1200 expressed like this, like 1 colon. So if you were to take 1 divided by 1200, you're going to get a number. It's kind of small, right? But that's basically what this is. If you were to mathematically evaluate this, you're going to get a small number. Here we have another representative fraction, 1 to 24,000, or on USGS topographic maps, it's expressed as 1 to 24,000 like this. So, but if we mathematically evaluate this expression, we're going to get a lot smaller number than that. This number is a larger number than that. This is a large scale map. That is basically a medium scale map. 1 to 100,000 or 1 to 250,000 or 1 to 1,000,000 are small scale maps. So when they're talking about scale, like this is about the scale of something that you would use for a town or portions of a city maybe, or a rural area. 1 to 24,000 is a 7.5 minute quads that cover 16 something like that, or 56 square miles. Are usually 7 by 8. 7 miles by 8 miles, so it's about 56 square miles. So this contains a larger geographic area, but there's not very much detail. This covers a smaller geographic area, but there's a lot more detail, like manhole covers and streets and sidewalks and homes and stuff like that. So that's what they're referring to as small scale here versus large scale here. This number is larger, that number is smaller. Alright, so let's see what they want us to do in scenario 1. UNESCO World Heritage Sites. You are creating a small scale map of the world, there's the key point, of the world, for displaying UNESCO, United Nations Educational, Scientific, and Cultural Organization, World Heritage Sites. World Heritage Sites are landmarks or areas that have been designated as having cultural, historical, scientific, or other form of significance. Which type of geometry would be most appropriate for World Heritage Sites? Okay, so let's think about this for a minute. I don't know how they're going to go on this, to be honest with you. However, let me tease out some details. So one of the things they say here, they say are landmarks or areas. All right. So we're dealing with a small scale map of the world. So are we going to be able to see an area on a small scale map of the world? Probably not. Okay, we're probably going to be dealing with a map that may be going in a portfolio or a brochure or something, and the best we're going to be able to do is put a point marker down to show what the distribution of UNESCO sites are. We probably are not going to be able to see see a line or a polygon. That being said, most of the organizations that work on stuff like this begin with polygons because they want to be able to create other kinds of data products that may show the actual aerial extent of one of these UNESCO sites. So, not that this is not a trick question. This is not a trick question, but the thing is, you have to consider what they're telling you what the answer is here, right? They're a small scale map of the world. So at a small scale, we're only going to be able to see points, and we can see we got the answer right. However, that's not really the way the real world works in the mapping industry. The way it would generally work is you're going to have a polygon that describes the actual extent, and then you're going to use a special part of that polygon called the centroid to drop a marker down that shows basically the center of where that polygon is, and you're going to use that point as the point for your map. Okay, so the idea being here is this: always collect the most accurate data you can, always collect the most accurate data possible, because you can always generalize and simplify. However, you cannot go backwards. If you only collect that information, and somebody comes along later and says, hey, I'd really like to have a map of the entire UNESCO park here, wherever, you won't be able to go through and figure out what the actual aerial extent is because you only have a point. But if you have the polygon that kind of demarcates the boundary of that UNESCO site, then you can create a point from that polygon, but you can't create the polygon from the point. Number 2 is our archaeological site. You're creating a map of archaeological sites within 2 kilometers of Stonehenge. So how far is 2 kilometers? It's about 1.5 miles. It's something like that. Let's see, it's a little over 1 mile. Archaeological sites are where archaeologists have been permitted to excavate a specific amount of ground, like 5 square meters, within a designated area. So I've been to Stonehenge. It's pretty cool. There's tons of archaeological sites. Like, you would not believe how big the area is actually. What they show you on TV is just a small smidgen of what that whole area is like. So which type of geometry should you use for archaeological sites? Well, they're saying excavate a specific amount of ground. Here we're talking about 5 square meters, so we're talking about an area within a designated area. So we could say lines, but the reality is the lines doesn't really give us anything but perimeter. What we really want is an area and perimeter. And to get both of those, we are going to use polygons. So for scenario 3, major roads, you're creating a map of Australia to show the national highway. The national highway is the major system of highways and motorways that connect the capital cities and regional centers of Australia's mainland states and provinces. Which type of geometry should you use for road features? Well, we're not talking about area, and we're not talking about points, but we are talking about lines, so that would be the obvious answer there. Alright, now we're going to investigate vector features. Alright, in this exercise you will explore the geometry and attributes of vector features using ArcGIS Pro. The data represents natural monuments, which are points, bicycle paths, which are lines, and natural reserves, which are polygons, in Salzburg, Austria. Alright, it should take us about 15 minutes, and to complete the exercise I need 3.2. So I've already downloaded the data. I'm going to go ahead and fire things up and bring everything up, so my next screen should show us where we're at. So I'm going to launch Pro. I have Pro open. I have already been signed in from a previous session, so I did not have to go through the sign-in process. In future videos, I think I do go through the process of signing in to Murray State. I wish they had this area promoted to a different level so it's more visible, because it's just as important as some of these other things, because usually, you know, you're going to start a new project, but the other thing that you're going to do is also continue working on a project. So visually, I think this ought to be promoted to a more visible status than relegated down here to this thing. So under 2C in this exercise, it says near recent projects, open another project. Well, here's recent projects, and it just seems like they, I don't know. User interface design and user experience design are two fields within computer science and kind of psychology that combine, and so you'll always find people that do software design a little differently, and sometimes it's the software engineers who decide on the layout, and it doesn't always make a lot of sense sometimes. So anyway, we're going to open another project, and then I'm going to go find my project, which is on my PC and here, and it's under my courses, and it's under ESRI, so it's going to be in a different place on your machine, so don't follow exactly what I'm doing, because my directory structure is going to be different. You have to follow your directory structure. So now I'm under Spatial Data Intro, and it wants me to open this. Now it says double click. I'm just going to single click and select OK and wait while it opens my project. Oh, no wonder it's hard to see. Alright, so we're going to investigate features as soon as my vector data loads. Alright, nice. So I can use my mouse wheel to zoom in and zoom out, and if I right click my left mouse button, I can drag it or move it around and reposition it. But let's see what the instructions want us to do. You will start by investigating point features. From the Map tab, ensure that the Explore tool is active. So from the Map tab, so here's Map, and the Explore tool is right here. So we're going to make sure it's active, and it is. On the map, click the tree symbol on the map. So here's our map display window. We're going to click a tree symbol. I'm going to pick the one way out here, just to ensure that I get the one that I want. And I've picked a natural monument called Hochstein. Alright, I'm going to expand my box so I can see kind of what's happening here. And that's about it. Alright, so we can see latitude, longitude coordinates. We are at So the east is the x and the north is the y. We are at 13.11 and some degrees east of the prime meridian. We are 47.83 degrees north of the equator. All right, so latitude, longitude. Also, we can see this down here at the bottom. And anything else to note? Not really. And we can see a scale, 1 to 66,400 essentially. And we can see that as I move the cursor around, these coordinates update. And as I zoom in, our scale changes, or zoom out, I'm sorry. And then if I zoom in, also it changes. Okay, this is our pop-up box. It's already been this database has already been pre-populated with information. If the pop-up does not appear, click the Explore Tool down arrow and select another tool option. So that's what they're saying us up here. We're doing the topmost layer. So in the topmost layer is actually the World Light Gray reference, and then the next layer is the natural monuments. So the way these things are ordered is this is the bottom, this is on top of the bottom, this is the next layer. So you think about them as kind of sheets of paper or just layers, right? So the one that's on top is the top layer, and then it goes down to the bottom layer. You can view vector attributes for each feature by clicking the feature on the map, or you can view all the attributes for the vector feature class at the same time using the attribute table. So we're going to close the pop-up. In the contents pane over here, right click the natural monuments layer. So we're going to select the layer, not the symbol, but the layer. And we're going to right click and choose attribute table. Alright, so the attribute table will appear below the map viewer. We can detach this, I believe. Yeah. So if you click the tab, you can move it, you can create a separate window and drag it somewhere. So we can look at the attribute table, and we can look at what the attributes are for all of these points. We can see that the object, ID, and shape fields are pre-populated, and then let's see here. Okay, we can open this up, and let's see, no key, category, deck, and RGL. I'm not sure what RGL is, but that doesn't mean anything. So we can go through and see what the other fields are. So you can right click one of these and summarize. I'm kind of getting ahead of myself, but you can, oh, that's not what I wanted. What I wanted was, let's drag that out there so we can see the whole thing. If we look at the fields, that's what I wanted. If we look at the fields, we can see if the field is visible, if it's read-only, like if we can edit it or not. We have the field name. We can give it an alias if we want, like if we don't like the name number, like I don't know what that is. Number is some type of ID number. So it's different from the object number because that's just created by the software. This number may be given by like a department or an agency within the government, and that's the way they identify different parks or forests or things like that. It's a user-defined value, in other words. So we know we can see what the data type is, whether it's a long integer, what kind of geometry. This is a double. It's a floating point. It's a and rather than double accuracy, double precision. This is text field. This is a long integer text again. We can check the box to see if we allow nulls, and we can see that the nulls are allowed. Null means you can leave the field blank. And the number format, and then there's some other things out there. Double precision is what this means. So single precision usually gives you maybe 3 decimal places to the right of the decimal point. Double precision usually is double that, like 6 to maybe 9. And you can sometimes the user can specify what the precision is. All right, let's get rid of that because I'm off the beaten path a little bit. All right, so now we're going to investigate polygon features. So let's close this, and we do have a polygon feature visible. It is a natural reserve right here. Click from the map tab in the selection group, click select. So here's our map tab, and so we have all these abilities, and we're going to choose select. Now we have options out here. We can do select by rectangle, polygon. We can draw a circle around, draw a lasso, which is a roughly defined polygon, a circle, a line, or we can trace. We're just going to do a rectangle. Actually, you can just do that and select it. That works as well too. And then we can do zoom to selection. So if we right click, we can say select to features. That's almost the same thing. Or we can say pan to selection, and then we can say zoom to, and then zoom right in. And so we can see that our scale down here is now 1 to about 6,000. So 6,000, it's about 1 to 30 feet. So 1 inch on the map equals about 30 inches on the ground, or I'm sorry. It's 1 to 30. So 1 inch on the map represents about 30 feet on the ground, I think. So what I do, that's about 6,000. So 6,000 inches divided by 12 inches results in about 300. I'm sorry, it results in 300. So 6,000 divided by 12 is 300. So 1 inch on the ground represents, or 1 inch on our map here represents about 300 feet on the ground. So that's my math on that. So I rounded up to make the math easier. What? That doesn't even make sense. Let me make back up. So 6,000 divided by 12 is not 300, it's 500. So it's 500 feet. I don't know where I got 300 from. So 60 divided by 12 is 5. So 6,000 divided by 12 is 500. So 1 inch on this map represents 500 feet. So ignore what I said earlier. I'm sorry, I wasn't thinking right. So anyway, we have this natural monument area selected. This is on the ribbon tab. Click the edit tab. So here's edit. Alright, so we have a new set of tools here. In the tools group, in the gallery, click edit vertices. So in the edit gallery, so in the tools group, this is the tools group. In the gallery, and that's what they're calling this is the gallery. Click edit vertices. So we're going to click that. Alright, so now we can see all these squares. That's probably where they started and ended. That red vertex right there, or the red node. And we have a tool group down here at the bottom. I'm gonna see if I can't drag this around. I may not be able to drag it. I guess not. Oh, I guess I can. Alright. I thought maybe I could drag that thing around and reposition it. Select the toolbar location and size. Oh, okay. So I can put it there if I want. Alright. Let's do that because it's easier to see. Polygons are 3 or more vertices. X and Y coordinates connected by lines, creating a closed shape. Each square on the polygon represents a vertex that was used to construct the polygon. The red square shows where the vertex was created last. So that's the last place they dropped a point. If you were to move one of the vertices, the shape of the polygon would change. On the ribbon, click the Map tab and then the Navigate group and click Explore. Okay, so they don't want us to move anything. We could, if we wanted to, move things around if we had to adjust. But I don't want to do anything like that. I'm just going to go back and leave things the way they are. So I'm using a keyboard shortcut. So if I move something, like I move that one, and then I move this one, I'm like, oh, that's not right. I can hit Control Z, and Control Z backs me out of that edit. All right. So now we're going to go back to the Map tab. We're going to go to the Navigate group, which is right here, and then click Explore. All right. Make sure that the polygon is still selected. Oh shoot. Alright, so let's go to select the polygon, and then go back to Navigate and Explore. Alright, so we're still selected. In the Contents pane, right click the Natural Reserve or the Natural Reserves layer and choose Attribute Table, Natural Reserves, and then right click and then choose Attribute Table. And we can see that when we've done a spatial selection in the map view, that we've also done a database selection within the attribute table. So we can see the attributes attached to that natural reserve or the nature reserve. So this is the Hammerauer Moor. Hammerauer. We can see in this attribute table we have an object ID, which is a software generated ID. We know that it's a polygon. That's also a software generated value. We have a no key, which is a user generated value. Everything here is basically user generated, except for these two, shape star and shape STLE are both, those are user generated as well. These are shape length and shape area are determined by the software when the feature is built. It's automatically generated. Okay, H for H, I think, is we close the attribute table. From the Map tab in the selection group, click Clear. In the Navigate group, click Bookmarks. So we have bookmarks. So if there's places on a map where you frequently want to go through and visit, you can set a bookmark. And in this case, we're going to choose the Salzburg, Austria bookmark to return to the initial extent of the map. Choose the Salzburg, this one here. So that's going to send us back to where we began. So now we're on to 5. Investigate line features. Now you will investigate the geometry and attributes of line features. From the Map tab in the selection group, click Select. So from the Map tab in the selection group, click Select. On the map, click one of the bicycle path features represented by the dashed green line. So again, I'm going to pick one that's easy to pick, like this one, and it's going to give me that bike path. And in the Contents pane, I'm going to select bicycle paths, point selection, and then zoom to selection. Okay, I don't think I read the directions. It says right click the bicycle paths layer. Point to selection and choose zoom to selection. See, that's what happens sometimes. There's so many detailed instructions on here. Sometimes at least I, and that's what happens a lot of times when I'm coaching students on how to work through these, is the points and the clicks can kind of get buried sometimes. So anyway, we've got the entire bike path now. The map zooms to the extent of the selected line. you will use an editing tool to investigate the geometry of the line feature. On the ribbon, click the Edit tab. So on the ribbon, Edit. In the Tools group, in the Gallery, select Edit Vertices. Alright, we can see a lot of vertices. Because the thing is, so if you think about the line and the polygon are mostly created sort of in similar ways. You have a start node and an end node, or a start vertex and an end vertex, and then you basically heads up digitize and create the line on screen perhaps, and then in a case where you have a bike path, it's just a line. It doesn't have any closure. With a polygon, you're going to have closure, and then you're going to tell Pro or whatever software that you're using, oh yeah, this is also a polygon, and then the software will go through and build the geometry behind it, behind the scenes. Lines are two or more connected vertices. If you were to move one of the vertices, the shape of the line would change, of course. F. From the Map tab, in the Navigate group, click Explore. So we're going to leave this selected. We're going to go back to the Map tab. We're going to click Explore. In the Contents pane, right-click Bicycle Paths and choose Attribute Table. Alright, so it's already selected from before, and now we're going to open up the Attribute Table. You could also use Control-T as the keyboard shortcut. So every one of those line segments is going to have an attribute, and it's going to have a record in this attribute table. So in this particular case, there's 76 line segments. So that means there's every line segment, you have a beginning vertex and an ending vertex, and then that ending vertex is the beginning vertex for the next line segment, and so on and so forth. So let's expand that out. Okay, so then we have all the typical ones we should expect. You're always going to have an object ID and a shape or some type of geometry associated with the feature that you're mapping, regardless of what software that you're using. In the Esri products, they have a field called object ID and shape. If you're using something else, you'll have to consult the documentation. Bezeichnung, this is probably the name of the bike path. Then we have an external number and external ID. These are probably user generated. We have a type, which is also potentially user generated. We have a length, which is software generated, and then the shape length, which is software generated. The shape STLE is most likely a user generated. Some human being created this field, and this field, and this field, and this field, and the type field. That was done by a human being. Alright, so now we've gone through that. From the Map tab in the Selection group, click Clear. And in the Navigate group, click Bookmarks. And go to the bigger view. Alright. Now it did not tell us, I don't think, to close the attribute table. I don't see it. So we're just going to leave it open and find out if we're supposed to close it later. Sometimes they forget to tell us that. So 6, investigate multi-part line features. A few of the line features in Bicycle Paths feature class are multi-part features, which means that their geometry is not connected, but they share the same attributes. You will investigate one of these multi-part features. First, you will select a specific multi-part feature. On the Map tab in the Selection group, select by attribute. So in the Map tab, in the Selection group, select by attributes. Alright, cool. So there's our select by attribute dialog box. And so basically what's happening here is people will say, well, I've never created a SQL query before, standard query language, SQL. And so that's kind of true, because maybe programmatically you have not written code to do it. But what this is a user interface where you get to build an SQL statement. And you can see there's a hint right here that says SQL. So what we're going to do is we'll build it, and then we're going to try to see if it will show us what the SQL statement resembles or looks like. So select by attributes. For input rows, verify the bicycle paths is selected. So yes, we do have bicycle paths selected. For selection type, verify the new selection. This is a new selection, meaning we don't have anything else previously selected. It's a brand new selection. Because if you don't have that, the idea is you can have a selected set, and then you could select results from your selected set, right? So if you scatter a bunch of Skittles on the desk, and you're like, well, I just want 12 of the 20, and you pull those 12 aside, then since those are selected, then you can select within that group of Skittles, like the red ones or the blue ones or the yellow ones or whatever, right? So under expression, see, here's expression. Create the following expression where bezeichnen is equal to Tauernrodwig. Alright, so we're going to go down here to Tauernrodwig. Yeah, whoops, nope, that's not it. Well, maybe it is. Tauernrodwig durch das Selektor. And then we're going, okay, so before we click apply, so this is what our SQL statement would look like. So we have bezeichnen equals Tauernrodwig durch das Selektor. I'm trying to do for German. I had German in high school, but never really got me anywhere. So now we're going to do an apply. And we do have features selected. So that's where we know we've done a good job. And let's see. Then we're going to close. I'll click OK. Close the select by attributes box. In the contents pane, right click bicycle paths, point to selection, and zoom to selection. So point to selection, zoom to selection. So you actually have to click on selection and then zoom to selection. Alright, so we can see we have a multi-path line here. So they're not connected, but they share the same attributes. And if we, so let's say we have one selected, and we can zoom to it, I think. And let's see. What we can do is, so if we do switch, what we're doing is we're just looking at no, that's not it either. Alright, well, we'll just zoom down. So here's this one. There is a way to look at just the, oh, here, down here. Yeah, that's it. So down here, you can look at just the one that you want to look at, just the record that you've picked. That's what I was looking for. Alright, so now we can look at the attributes. We can look at the external number, the internal ID, the name, the polyline name. So it's a polyline, which is a special form of a line. The polyline means you can have disparate lines that all share the same attributes. So for whatever reason they don't have something here, or maybe it has a different name, maybe it's managed by different people, maybe these are all managed by one group and the connecting legs of the bike path are managed by other organizations, or there may be no bike path there. Anyway, we know it's 34,827 something long. It's in Austria, so it's probably meters. It's my guess. Could be centimeters, I'm not exactly sure. But we do know one thing. We do know the length, the shape length is user generated. I mean, software generated. It's automatically generated. And this is a user field, and that's probably also a user as well too. All right. Now we're down to I. Show selected records. Oh, I already did that. And And then now you can see the single record, and if you're continuing to the next exercise, keep this open, otherwise close. Well, I'm going to keep it open. And I'm going to move the screen back. Oh, and now we have a quiz. So let's take a quiz. Alright, each row in an attribute table represents one vertex of a feature on the map. That's not true. Each row represents either a point, a line, or a line segment actually, or a polygon. So this part here is not appropriate. One vertex, no, that's false. Attributes for vector features can be automatically generated or user defined. That is true. There's going to be some features that are automatically generated all the time, and then you have the option of adding more. Which characteristic describes a line feature? 3 or more connected vertices creating a closed ring. That's not true. So the reason why that's not true is this part is true. 3 or more connected vertices creating a closed ring. Well, that's a polygon, and that's not a line. So, I mean, you can have a closed ring, and it could represent like some type of weird road or bike path or something, but let's see what other options we have. A line feature, 2 or more connected vertices. Well, that is absolutely true. So this is a better option than this option. 3 or more vertices. Well, you can have a single line feature that's 2 vertices. It's a line, a point, a beginning, and an end. So it can't be this one. And a single vertex is not a line, it's a point. So the best option is this one. These two are invalid, and this one kind of sounds reasonable, but this one's the best option. You are creating a large-scale map, 1 to 17,000, of the oldest parts of Paris, France, that will highlight the locations of bridges and docks along the Seine River. Which vector geometry should you use to represent the river? So large scale, 1 to 17. So let me think about that for a second. You probably, so it's large scale, parts of France. So you're going to be kind of zoomed in at kind of a residential level. So you probably want a, let's see, a multi-point feature. No. So a line representing the river, no, because you're going to see the river actually at a scale of 1 to 17,000. You're going to see the river. You're going to see both banks of the river. 1 to 7. So if we divide 17,000 by 12 to get feet, that's about 1 inch on the ground represents about, let's see, 17 divided by 5. Is about 3,000, so we're looking at about 1 to 3,000 feet. So yeah, it's not going to be a line. A multi-point feature representing this. We're not talking about points either. So these two are invalid. A multi-part polygon representing the river. Well, we haven't even talked about multi-part polygons. So that's probably not valid either. So we're just going to stick with a polygon representing the river. So again, remember what the scale is. The scale is large scale. So we're looking at a very specific portion of the oldest parts of Paris. So we're going to be down. So if you need to, hang on a second. Let's do this. All right, so what I have done here to help us kind of think about this problem is I've gone to a secondary source. So that's what happens sometimes. If you have questions about how things align or how large or small things are, or you question the size of your area, the scale of things, use the tools that you have around you to your advantage. So in this particular case, I have launched Google Earth Pro. In Pro, I can activate the scale legend. I can turn the scale legend on and off. So I'm going to put the scale legend on. I don't think I really need an overview map, but what the heck? Nope, I don't want it. Overview map now. I don't really, the grid's kind of distracting, so I'm going to do that. So the scale is down here. So at our current altitude of 14,000 feet, basically. So imagine you're like in an airplane hovering or a helicopter hovering over downtown Paris at 14,000 feet. So the scale of this is, so we have a scale here, it starts there, ends there. It's about 3,109 feet. So just say 3,000 feet. All right, so here's what I'm going to do. I'm going to go to here. I'm going to, and the question had dealt with 17. The scale was 1 to 17,000, right? So I'm going to get my calculator out. I'm going to convert 17,000 inches, divide by, there's 12 inches in a foot. So roughly the scale needs to be 1,416, or about 1,400. Don't worry about, just round up and get kind of close, right? So I want this number to be around 14,000. So I'm going to continue to zoom in, and I'm going to try to there's a lot of 3D buildings out there, so that's kind of cool, but it's also kind of distracting. Whoops, now I'm at 1,100. Now I'm at 1,400. All right, that's about right. So at this particular scale, so it's 1 inch on the ground represents about 1,400 feet. That's what we're looking at. So a line does not do the Seine River justice here. We're going to have to do a polygon, right? At this scale, we're probably doing large property as polygons too, and like the Grand Palais and the Palais de Concorde are going to be polygons too. So we're going to do a polygon here. So I wanted to show you how this scale worked, so that we could see what it is we're trying to map, and then we can remove this and then go back to our question about this. So so basically what you do with these scales is, so if 1 inch represents 17,000 inches. So 1 inch on the map represents 17,000 feet in the real world. So, but 17,000 feet, I mean 17,000 inches, we have to convert that number to something that means something. So 17,000 inches, well, there's 12 inches in a foot. 17,000 divided by 12 gets us around 14. So anyway, 1,400 feet. And so a polygon is going to be our best bet. Which statement is true? Local parks should be represented by polygons at small scales. Well, small scales means like 1 to 24, 1 to 50, and parks aren't really going to show up very well at that scale. Cities should be represented by point features at large scales, so that's not good either, because we just saw it. We just saw large scales, and Paris is huge at large scales, so that's not good either. This is not good. Don't worry about that. That's not our answer. Each real-world feature can be represented by a single geometry type, point, line, polygon in a map. Well, that's not a bad answer, because that's true. A point can represent a city depending on the scale. A polygon can represent a city depending on the scale. I don't know. This isn't horrible, but I think maybe let's see if there's something else. Real-world features may be represented by different geometries at different scales. Okay, this is the answer I was looking for, because this is true. This is true. This sounds sort of good, but the line is bothersome. This is not true, and that's not true. All right, so let's submit and see how well we did. All right, we got them all right. Cool. All right, I'm going to pause the video. $30 minutes. All right. doesn't start off that way, but eventually it filters down. So like I usually take coupons for like a box size. Like, and it was for a free box of the 4 or the 12 or whatever. So I'm like, okay, well. Or you'll get one that's like buy one get one free on like I'll get like the packaged rice. Buy one get one free on rice. They're on a budget. Oh really?
Oh yeah.
I did not know that. Just not for companionship.
Well, you can get it from her house.
Yeah.
I did it from my head. She lives straight from her house. It's like, last month I was trying to use like 4 cents on the count.
Yeah, I don't use the app so much, but I like to actually go in the store and poke around. I rely so funny thing is I rely on other people to use the apps, but I don't have to see them shopping. But I'm like, oh, these people all use the apps, so I feel safe. They're like, I'm never gonna run across them ever, thank God.
Well, it's like my parents, they always do the stuff. I like to just put myself in the game. But it's kind of annoying because the people that do the pickup orders, when you look at the little parts,
Yeah, yeah.
have no spatial awareness.
Yeah,
Oh, it's
yeah.
awful.
See, that's the thing. It's like I get too fussy about how things are organized. And, if people will say, "Well, you bag before and everything," I'm like, "Well, I used to work for Walmart way back in the day." So I'm like, "Yeah, I use that." And I'm also anal about how things get stacked.
It's like they put like bread and they get charged.
Yeah, or like hamburger buns and stuff like that. It's like clearly these people have never lived on their own or done their own grocery shopping or been responsible for making dinners for anybody other than themselves. Because they're like, actually heard people be like, you know what, I used to not give a shit when I was packing groceries. Now that I'm on my own, I realize I was kind of wasn't really paying attention to how this jackwagon just packed my milk and my hamburger buns together. I'm like, why'd you do that? I'm like, oh man, I used to do that. It's amazing how that kind of stuff makes you self-aware of things after the fact. All right. Okay, now it is. All right. So, well, I'm at about an hour and 15 minutes. And so obviously these videos take longer than the actual lesson. But I'm doing this just so that we can cover the bases and you can get a better understanding of how these classes work and just a better understanding of my narration as somebody who's been doing this for a while. Alright, so now let's explore the raster data model. The raster data model represents the surface of the Earth as a grid of equally sized cells. So an individual cell represents a portion of the Earth, such as a square meter or a square mile. Each cell contains the information for that part of the Earth. Okay, so here's the deal on that. It says equally sized cells. You get to determine what the cell size is. Like usually when you sit down to create a grid or work with a raster model, there's two things that are going to happen. If it's you can have a user-defined grid and you get to decide what your sample size is or what your resolution is. So when they're talking about square meter or square mile, they're talking a little bit about the resolution of your data. And you also need to bear this in mind too, is the more squares you have, the more hard drive space you consume, the more data rich your file is going to be and the larger your file is going to be. Also, there's a lot of work that goes into determining what your cell size should be. And again, it goes back to the idea of what I said earlier about you can always generalize up, but you can't take something like if you measure something at a square mile and you assign an attribute to that something at a square mile resolution, you cannot then go back and say, oh, I really messed up. I really need to have a square kilometer or a square feet or whatever, because you can't upsample or your resolution to get something better. You're stuck with it. So most of the time what you want to do is you want to use the best available data and generalize up, because you can't go backwards. The term raster and image are often used interchangeably, but they're not the same thing. I kind of think as rasters or images as being a subset of raster, but raster is not a subset of an image. An image can be a raster, but a raster does not have to be an image, if that makes sense. An image is a 2D pictorial representation. Well, that's also kind of what a raster is. While a raster is a data model used to store information in rows and columns of cells. That's also what's happening in a image as well too. So the thing is, it has to do with how the data is gathered and obtained. So like it says here, all images are rasters, but not all rasters are images. For example, a data set that shows rainfall levels is considered a raster, but it is not an image. Well, the thing is, within the GIS realm, within the remote sensing realm, that's true. But if you are in the graphic art and design realm, it doesn't matter, because there's still information in that image. So as a person who does graphic art and design outside of the GIS remote sensing, I have to play the GIS game and the remote sensing game, but in the graphic design realm, they don't care whether it's an image or a data model. It's kind of when push comes to shove, at the end of the day, they're almost the same thing. This is an image of a raster, if that makes any sense. So some graphic designer put all this stuff together and put a caption down here, and we have a nice pretty picture, but this picture is a raster, but it's also an image. It's an image of a raster. So, and there's data there. Even if it's an image, there's still rows and columns. If this is a JPEG, if this is a TIFF, if this is a PNG file, those cells in there have a value. Anyway, so just bear in mind, you're working within the GIS and remote sensing realm here, so you've got to keep yourself fenced in with the nomenclature. Some rasters may contain several pieces of information called bands. So yeah, in remote sensing, when you have a layer, when you have the blue band and the red band and the green band, those are all rasters. They're rows and columns, and every cell in that rows and column has a bit of information associated with it. The band represents data captured at certain wavelengths. For example, a satellite might capture an image that contains 8 bands of information. So it's 8 channels. Sometimes you'll see it referred to as 8 channels of information, but basically what you're looking at is 8 wavelengths of light, of radiation, 8 wavelengths of electromagnetic radiation. So it may be blue, green, red. It may be a couple bands of red, maybe a couple blue wavelengths. It may be infrared, which is not thermal. Thermal doesn't happen until further down the electromagnetic spectrum. Then you could have thermal once you go down there, but you can also have infrared and ultraviolet. Yeah, so it gets pretty cool and pretty crazy. So the thing is that this raster data model also applies to space-based telescopes, like the James Webb Space Telescope, Chandra X-ray Telescope, Hubble, anything that collects imagery. Let's see what happens when we click next. Alright, so this is what satellite imagery looks like, and this is the way most of the imagery collected by space-based sensing devices work. Like they're looking at very specific portions of the electromagnetic spectrum. It may be the helium, it may be hydrogen, it may be oxygen, it may be the blue band, it may be the red band, it may be the green band. And so when you look at them individually, they're just going to be black and white, because what they're basically doing is they're converting the electrical response on the sensor to a digital number, usually between 0 to 255, for example. And then when you look at that, you're just looking at a reflectance value that's been converted to a digital number. And then the software looks at it and says, okay, we're going to make the 255 values really bright, and we're going to make the 0 values black, and then everything in between is going to be a grayscale. But it's based off the reflectance value of whatever it is coming in and hitting the sensor. So when it says red, this is actually not red. It's not going to look red. It's going to look black and white, grayscale. Same with green, same with blue, same. Band 5 is infrared usually. And then band 1 is usually blue, band 2 is usually green, band 3 is usually red, and band 4 is usually infrared. So I see what they're doing here, but they've taken a little bit of creative liberties here for the demonstration purposes. And then what we do with the software is we take a multi-band image like this. While most monitors can only display 3 colors at a time, and so what they do is the electronics within our monitor, for example, varies the electrical output, so the green's a little less bright, and the blue's a little dimmer, a little brighter, and red's super bright. And so each pixel on our screen gets a signal that says, do these, shine blue like this, green like this, and red like this. And when those colors come together, then it creates when those 3 colors come together, it creates another color, right? So what we generally do is we'll take something like band 2, band 3, and band 4, and we'll say, okay, we want the blue part of the electromagnetic spectrum. We want to assign that to the red color on our display. We're going to take green and assign it to the green color on our display. And we're going to take blue and assign it to the blue color on our display. And the software allows us to do that. So that's why, like in Pro and in products like Erdas Imagine, and even in software products like GIMP or Blender or other image processing packages, you can take those layers and say, hey, this is red, this is green, this is blue, blend them together in the way that I tell you, and then you have this new colorful picture. And it's called a false color composite when that happens. So it's kind of cool, because once you learn how to do these techniques, you can just jump over to satellite imagery and start analyzing satellite imagery from James Webb Space Telescope or the Chandra X-ray. It's pretty cool. All right. Raster attributes. Raster information is stored in the cells that make up the raster. Raster attributes are usually created automatically by sensors rather than by users. In a multi-band raster, each cell will contain attributes from each band of the raster. The attribute for each cell is determined by taking average value of the entire space that cell covers. So rasters with small cells, which cover a small amount of space, provide greater detail than rasters with large cells covering a larger amount of space. The size of the cell is called the raster's resolution. Rasters with several bands of information may show more than one attribute. Yeah. So it goes back to what I said earlier on the previous slide. Every cell is given a value, and it has to deal with the electromagnetic energy coming in. It hits the sensor, it tickles it a little bit to generate a little bit of a voltage, and that voltage is then converted over to a digital number, and then that digital number is used to help display the image. And then what a user does, it says raster attributes are usually created automatically by sensors rather than by users. Well, that's kind of true. users will generally go through and classify an image, and when you classify an image, basically what you're doing is you're saying everything with a digital number that looks like this is the value of this, and value of this is grassland. Everything with a digital number that looks like this or this or this is water. Everything with a digital number like this or this looks like is a snowfield or a glacier. And so then we can go through and start assigning attributes to groups of cells through a process called classification. Now we don't have to do this from satellite information. If we're just looking at landscape information, maybe we have a cluster of temperature sensors out in the field, and so we can lay a mesh. Another way of looking at this is a grid a mesh is another form of a grid. We can lay a mesh over our landscape, and one cell of that mesh or that grid can have a temperature, and another cell over here can have a temperature, and pretty soon we map all those temperatures out, and then we can do things like interpolation and give values to other cells along the way, because we're interpolating the value of temperature with distance according to usually there's some formula that's been programmed into an algorithm to assign values. Same thing works with watershed analysis. You have water that runs through sensors and devices and things like that to determine what the runoff is. You have slope and aspect associated with a watershed, and so those factors go into determining how much water flows through a watershed. And with like watershed analysis, you can use the grid data model to kind of determine flow and direction of flow and things like that. It gets more complicated. If there is more than one band of information in a raster, each cell may contain more than one value. For example, a color raster image, there are different bands for red, green, and blue. So like in a JPEG or a TIFF or a PNG file, each one of those cells tells the software how to determine the color for that particular cell. So that's how these color things show up, and that's how you have like 256-bit color or 16,000 shades of color or 23 million shades of color, those types of things. Alright, so raster data types. There are many types of raster data which are used for various purposes. So we have raster data. The raster data model can be used to store continuous data, such as rainfall, temperature, or elevation. In this temperature raster, the average temperature throughout the world in the month of July is shown. So then we have discrete data. So discrete data is basically like this soils raster. The different soil types in Kenya and the surrounding area are mapped using raster data. So basically what you're looking at here is a soil map where the polygons have been converted over to a raster, and all those cells have been coded with the soil value. So why would you want to do this? So basically what you're doing is it's really easy to do something called map algebra on grid, because if all of your grid data are referenced to each other, and you lay one grid down on top of another grid and all those cells and everything line up, then you can just basically write yourself a model or write yourself an algorithm that says if cell 1 1 or you say the value of this cell plus the value of this cell minus the value of this cell divided by the value of this cell times the square root of the value of this cell, give me the results. Then you can do that map algebra and it calculates all those things, and then your analysis can then carry forward, because now you have a value attached. You have a new value attached to a new grid, and now you have a landslide susceptibility model or something like that. But that's why discrete data is and grids work really well for doing this kind of analysis, is because it's really easy to perform operations on one grid versus another grid. So then we have imagery, which is produced using a camera or other sensor, and it is a common type of continuous raster data that can be used in GIS maps. This image is a satellite photo used as a base map showing Westminster in London, England. Other types of imagery include aerial and drone imagery, but it's all camera-based unless you're looking at, yeah, it's pretty much all digital optics. Existing print maps can be scanned and stored as rasters. Scanned maps may appear to contain vector data, but they're just actually really just a static raster map. So if we were to zoom in, I don't think I can zoom in on this, but you could actually see the little pixels, the little cells of each of this if I could zoom in. That's why you get these little blocky, like if you look at the Massey, it looks blocky. If I zoom in, let's zoom in. Do, 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 do. Alright. Alright, I guess maybe, where did it go? And I guess the way they have this screen code, or this thing coded, it doesn't work to zoom in. Alright. But anyway, you'll have to trust me on that one. Videos may also be considered to be a type of raster and stored in a GIS, and that's true. You can have something called a binary large object, which is a large image. In Pro, you can create mosaic data sets of rasters, which allow you to stitch imagery together to create a larger raster, or create a catalog of overlapping rasters of different resolutions. You can also use raster products to organize and view information from different bands in a raster. Alright, investigate raster data. I already have the data. I'm going to move my screen over. And I'm going to bring up Pro again. I'm going to close this project. I'm not going to save it. I'm just going to, I can't close it? Alright. I'm going to open another project. And I'm going to go into the well, maybe it's already in there. I just didn't pay attention. Alright, we're going to close that. At the top of the map view, close the vector data map. Alright, we'll do that. Alright. In the catalog pane, expand maps. So in the catalog pane, in the catalog pane, it says expand maps. And then we have raster data. And it says double click the raster data to open it. Alright, we'll do that. Alright, don't worry about that error that comes up. It says the datum transformation cannot be found. The data may draw with an offset. We don't care at this point. We're just looking at this. What's up? Do I have a pixel out on my screen? No. Alright. Investigate a single band raster. So we can tell this is probably a single band raster because it just has black and white values. Alright, so it says from the map tab, ensure explore tool is active. It is. On the raster, click one or two of the darkest areas to open up a pop-up. On the raster, so on the map view, click one or two of the darkest areas. We'll just click right there. Alright. The stretch pixel value is 308. And then we'll go down here and pick a white area. And this stretch pixel value is 1972. So what does that mean? Well, what it's done is it's taking the original values, which were somewhere probably between 0 and 256, and in order to create a better image with more contrast, it's expanded those values out to cover a greater range of white and black values. The darker areas are lowlands and the white areas are uplands. Alright, now we can close this pop-up. You will change the symbology of the raster so you can see individual cells more clearly. In the contents pane, right-click the dem.tif and choose symbology. So we're going to right-click here and choose symbology. Alright. In the symbology pane, for the color scheme, click the down arrow and then check the show names box. Alright, so let's see. Click color scheme, show names, and then we want the elevation 1. Elevation 1. Well, these are in alphabetical order, so there's that one. Alright, pretty. The raster is symbolized using several colors to represent elevation values. So I'm going to guess that the lowland areas are around 300 units, and whatever the units are, and then the upper values, the gray ones up here, are 2,307 is probably the highest point, whatever the units are. Zoom to an area of the data set where the color transitions from dark to light until you can alright, dark to light. Alright, so here we go. Here's dark to light over here. It's gonna take a minute probably. Ah, there we go. So we can see those pixels, right? There they are. They look kind of strange. They don't look like squares. They look like rectangles to me. Alright. So you can see the cells of this data set. At that particular scale, they look pretty clean and neat. But when you zoom in, like I'm at 1 to 7,000. There's 1 to 4,000. 4,600. And then there's one, that's 1 to 2,000 basically. So if that's about 1 to 100 feet, because if we divide 1,200 by 12, we get 100, right? Alright, cool. On the raster, in one of the cells, click the upper left corner. So let's zoom in to a better area here. Alright. So, okay, here's a square. It looks like a optical illusion a little bit, but these are squares now. On this raster, click in one of the cells, click the upper left corner. So here's, I'm going to pick this one. Upper left. Alright. If necessary, move the pop-up away from the place clicked. In the same cell, click the lower right corner. So I'm hoping this is the same one. And it says click the lower right corner. Okay. Notice the value that is displayed in the pop-up. 1022. Okay, stop. So if I choose this one, let's make sure. Choose the upper left. That's 1027. And the lower right, 1022. Okay. Alright, now we're going to investigate a multi-band raster. From the Maps tab in the Navigate group, click Bookmarks and choose Multi-Band Topo Bookmark. Multi-band Topo Bookmark. Alright. Oh, we're in New Zealand. This map is a raster of a scanned topographic map of Wellington, New Zealand. The raster displays in color by default, indicating that it is a multi-band raster. By default, rasters with a single band of information display in grayscale. The multiple bands of information in this raster are not from several sensors, but from several color values. On the raster, zoom to the word Wellington. All right, we're going to zoom over here. We can see that it's kind of has a zigzag look to it. As you zoom closer to the raster, you come closer to viewing it at the resolution at which the map was scanned, so the symbols and labels become easier to read. The map seems to use vector data, streets in orange, building footprints in black, elevation contour lines in red, but it is simply a photo of the original data and stored in raster format. Click one of the black areas. Alright, right there. Red, green, blue is 0, so it's going to be black. Cool. Click one of the other colors. So let's zoom in. We'll click this orange. 241, 145, and 0. This is kind of the way the eyedropper tool works on other graphics packages. It's going out there and picking up what the RGB value for that screen pixel is. This is not doing that thing. This is going through and looking at the actual cell within the data set. And so the cell within the grid, within the raster, says display red with 241, green at 145, and blue at 0. And alpha is usually a transparency, like intensity sort of. Alright. And then we're done. Click next, and we're going to take a quiz. Alright. Raster attributes are usually user defined. Ooh. I mean, usually is the key word there, not usually. So I'm going to say false. Raster attributes are usually given by the software. We can come through later and add more, but they start off by being defined by the software. Each pixel of a raster contains attribute information. That is true. It contains something. There's usually a digital number, color value, or something attached to each pixel. So what they're saying when they didn't really talk about this, I don't think. Maybe I missed it. But this pixel is the cell. It's an individual cell within a raster set. Which item can be used to manage raster data? Well, we can. A spectral band is not a management. It's just a data. Shapefile is not a. You can have raster data in a shapefile actually. I'm not exactly sure that's a bad example, but they didn't bring that up, and since they didn't bring it up, we can't really use it as a viable answer. LiDAR is another type of data. It's not a way to manage raster data. So I'm going to say a mosaic data set. Which statement is true about raster data models? Okay. The raster data model represents discrete features on the Earth's surface as points, lines, and polygons. That is not true. We can eliminate this one. The raster data model represents the Earth's surface as a grid of equally sized cells. That's potentially true. So let's just hang on to that one and investigate the remaining two. The raster data model uses different size cells to represent different features on the Earth's surface. This is false. The raster data model represents continuous features on the Earth's surface as points, lines, and polygons. This is also false. So we're not dealing with points, lines, and polygons. We're dealing with a grid. We have to a raster data model uses the same size cells. Like once you define, you'll never have a grid where like half the grid is this size cell and the other half the grid is cells that are a different size. Everything within one grid is the same size. Now if you have another grid, you can increase or decrease the size of those cells, usually to match previously existing grids. You know, either they'll be twice as large or a quarter as large or half as large, you know, or a quarter of large. And you can do that on a per feature basis. Like if you're going to do forest one way and water another way and grassland or pasture land on a third way, that's okay because they're individual grids, but you never have a grid that has different values for cells throughout different size cells for one feature. And you usually don't have multiple features in a grid either. So you might have a classification, but it's basically one feature, and that one feature is land use. Now you might be able to categorize, grassland, cropland, pasture land, water, gravel pit, mined land, but those are all different categories of a single feature, and that single feature is land cover. So you'll get used to this as things go on, but so this is not correct. So the only one that's correct here is the second one. And I'm going to submit and go on, and we got them all right. All right, so we are done. We can evaluate the course, we can view, print our certificate, or we can continue learning. I'm going to go view and print my certificate. So I took about 17 minutes longer, and we can see that my introduction to spatial data is confirmed, and I have my certificate, and there it is. And I'm going to save those. It says 1 hour and 30 minutes, so that's what they allot for the course. They probably ought to allot more like 2 hours, because if you're not familiar with the software or the terminology, all that kind of stuff, it gets more complicated. But so it took me almost 2 hours and 47 minutes to do this. But as you can see, I talk a lot. So anyway, I hope this helps. Now if I go back and look at my learning plan, I'm 67. Actually, I may have to refresh this because all right, I'm 69% of the way through. And I've got to do querying, and I've got to do getting started, and I've got to do map layout and online basics. But yeah, all right, I hope this video has helped, and watch for future videos. So yeah, all right. Until next time, everybody, have a good week.